But then we have to multiply by the new power, or the reciprocal of the new power, so we multiply by 2. So we're back to 1/2. And this was, I don't know, I just made that easy. I just did this. 1/2 power, and then that would be from 1 to 3. Now, I was particular on something that I kind of warned you about, but I maybe didn't emphasize enough, is on some of the problems like number 4, when it was an exact length, or number 6, an exact volume, I wasn't looking for the decimal approximation. Okay, this one ends up being, well, you get like root 12 minus root 4, 2, and then all that over 2. So that works. Simplified, that ends up being, remember there's a common, or not a common factor, excuse me, a perfect square factor of 12. That is 2, so we'd have 2 root 3 minus 2 over 2, and then that would just divide to be root 3 minus 1, which is, I don't know, 0.8 something. I forget. No, 0.7. Something around. Okay. There were just problems with, it's a fairly easy integration, but like lots of people tripping up over that. I don't know, getting tired, I guess, but I just wanted to test something. All right, number 8. We had a shape that had a circular base, and the cross sections perpendicular to the base were squares. So I did it this way. Those are my cross sections. Those are squares. So my integral for the volume is going to be whatever the side length squared is. And then if I take cross sections that way, they'll be dx. I just got to figure out what the side length is. And the side length is this distance across the circle, which isn't always the diameter of the circle, 8, and it is once, and never again. So we have to figure that out. And so we'll use the equation of a circle. The equation of that circle is x squared plus y squared equals 16. And so solving that, y would equal the square root of 16 minus x squared. So if I do that in my integral, that's going to work out pretty nice as an integral. I'm just going to integrate 16 minus x squared. And then I need to integrate it for all the x values, so that goes from -4 to 4. Okay, and you know, I go through and take the test once, and then I just decided to use that as a key. That's what mine looks like, because I had to redo it a couple times. So, yeah, I don't know what I was doing on this one. I had a hard time with it too. Anyway, getting the wrong equation for a circle, and then the wrong bounds, and everything. Now I'm not even sure which one's the right answer, because I'm not in the middle of it right now. Is it 4 times 88 over 3? Anyway. Oh, I'm missing something very important on this, aren't I? You're all shaking your head because some of you have those points for it, yes. Right? This is not the, sorry, this is y, but that's the value from the y-axis up. See what I'm doing here? I'm having a hard time with this. And so the side length is twice that distance, because I've got to go down as well. Okay. Sorry, I'm looking at this and seeing a 4 pop out, and I'm like, where's that 4 coming from? And that's where it comes from. Then as I square that, I get 4 from this 2 squared, and then times the integral 16 minus x squared dx. Okay. I don't know. Any questions there? Lingering doubts? I think a handful of people got that question right. It was not many. Lots of people got it wrong. But notice that that shape isn't a cylinder, right? A cylinder, when we take cross sections of a cylinder perpendicular to the base, we don't get squares. Unless the height happens to be the same as the, even then you'd only get one square. You get rectangles most of the time. Because this thickness would be different than the height, except for maybe once or twice, right? So you'd end up with lots of rectangles too. Okay. Oh no, that's the wrong one. 9, yeah, let's set up 9 as well. So 9 we were doing surface area that a lot of people forgot how to do. Like a lot of people did volume or something, I don't know. We had this shape that was like this from a square root curve. And we were going to rotate it around the x-axis, so like that. You know, so we get some shape like this, and we're finding the surface area, not the volume. Now, we technically can do this dx or dy. I chose to do it dx. Everything was set up that way. If I chose to do it dx, then my bounds are 1 to 5, that's given. And then I need some kind of radius, right? So my radius is going to be, in this case, just a y value. So it's going to be the function. Okay, and so I'm going to have 2 pi times the radius. It's 1 minus 4x. And then times, overall, remember, now I have to do my f of x is equal to this square root. And so f prime of x is equal to 1/2, 1 plus 4x to the negative 1/2, times the chain rule, so times 4. Okay, and so that'll give me a 2 coefficient out here, and if I do f prime of x squared, then I end up, so I have 4 times 1/2 is 2, but then I'm going to square that, so I'll end up with a 4 there on the top, and then that'll be 1 plus 4x in the denominator. Okay, so then I'm going to add 1 plus 4 over 1 plus 4x. What's that?
I can figure out how to solve that integral.
Well, I've got 2 square roots, right? So I can just multiply what's inside the square roots. And if I multiply what's inside the square roots, I can distribute the 1 plus 4x to both terms. And so I'll get 2 pi times the integral from 1 to 5 of 1 square root of 1 plus 4x, that's 1 plus 4x times 1, and then plus 4. Because 1 plus 4x times 4 over 1 plus 4x is just 4. And now I have something that's very much linear inside my square root, which means simple u substitution. And if that sounds insulting, just remember it's simple among u substitutions, right? There you go. Right, we're not doing a weird function and then having some weird du. We're doing u equals 5 plus 4x. Okay, and so du would just be 4 dx. And so we'll get a constant out of this, and we have a pi over 2 instead of a 2 pi. So we get, let's see, pi over 2 times, then we'd have 5 plus 4x. Instead of to the 1/2, I got to power that up, so 3/2. And then I multiply by the reciprocal of the new power, so times 2/3. And then, yeah, sorry, I don't know why I have pi over 4 written there. That would be pi over 2. When I take that 4 and divide it by the 2 pi. Okay, and then I have to evaluate that from 1 to 5. Okay, that turns out actually you can do an exact value on that if you really want. I don't think I asked for it this time. But that works out nice because I have 25 to the 3/2 power, and square root of 25 is 5. Right, so I just get 125 there. And then I have, if I put in 1, 5 plus 4 is 9. 9 to the 3/2 power is square root of 9 cubed, so that's easy. That's 27. And so, right, I end up with like 98 pi over 3. And then, whatever, that was 102.63 rounded to the nearest hundred. But anyway, there's that. Okay, number 10, let's say one word about you. I gave you the distribution function. You're trying to find the probability that the wait time is longer than 4 minutes. And so all you have to do is integrate from 4 to infinity on that probability density function. Like, this was literally the solution of the problem. Okay, now I know there's some limits and things we're supposed to do. What happens if I do my u substitution and let u equal negative 0.4x so that I can end up doing e to the u? Well, du equals negative 0.4 dx. And we're close to having that, right? We've got the constant part already, except for the negative sign. So this integrates to negative e to the negative 0.4x. And then I've got to evaluate that from 4 to infinity, which means I have to do a limit, but the limit as whatever letter goes to infinity here, that ends up being 0 because I've got e to a negative power. And so then I just have minus, I just end up with e to the negative 1.6 power. Okay, which honestly to me makes more sense as a decimal since I'm doing probability, so that's like 0.201, blah, 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 blah. Okay. Which of course I know off the top of my head because I wrote it down on my paper. Okay, but the biggest questions were either people, I don't know, I mean a lot of people did 0 to 4, which I actually did as well. See, I've got a whole line there like where I did the right one. I don't know why, but yeah, I did 0 to 4. Right, which we would be able to get, it's going to be a 1 minus that. It's the rest of the probability. Okay, so it's 0.798 or something like that. A lot of people were trying to work in the 2.5 for that was the mean. 2.5 is really how I got to 0.4, but maybe if we would have spent more time on exponential functions, I maybe would have asked you to get on your own, but since we didn't spend enough time on that, I didn't, and so I just gave you that function, but I gave you the information too. So 2.5 was sort of a distractor number in this case, I guess. And then the other thing is I got a lot of like 0.6 e to the powers here, where we multiplied by the extra 0.4 instead of divided by it. So, watch you substitutions. Choice ones went okay. Some of you decided that consumer surplus was really easy, and then you failed to realize that P actually stands for price, and so when I tell you the selling price is 280, I'm not giving you a value of X, I'm giving you a value of P. That was the most common mistake on that one.
I got a lot of money.
Some of you, when doing hydrostatic force, were trying to do it the physics way, where you just sort of multiply by the entire area of the plate, but then you fail to multiply by the right distance because you multiplied by the distance at the bottom of the plate, not the distance to the centroid, from the depth of the centroid. If you're going to do it the physics way, you got to at least do the physics way right, which means you need to know the centroid of the circle, or the triangle. Okay, and those of you that did whatever the last one, cardiac output, that's pretty straightforward. There were a couple mistakes, but some of it was frigging delta H over 3 or something. And then some of you forgot to look at the formula on the back here that had that the integral was in the denominator of a fraction. You had to do something to the other. Anyway, lots of fun grading. I graded the last 2 pages in a brake shop while my car was getting new brakes. A 2-hour wait. It was thrilling, but it was really nice to finally have it done. And to not have my brakes maybe this horrible driving. That was awesome. Okay. We gotta do a 30-minute lesson, right?
No. Even lesson. Still on break time.
So the survey, right? In this section, it was about 34% of respondents in either category, either doing Thursday or Friday lab sessions. And in my later class, there was a 1-person difference. Favoring Friday instead of Thursday. So I'm still a little bit up in the air whether I'm going to do Thursday or Friday. Sounds like we're going to do lab sessions instead of just taking a day off. So, and then everybody wanted homework on, not everybody, but the majority of us for homework on due on Sundays. So we'll do that. That'll mess up the grades this week, but then because I think the grader has time to do it like Saturday, Sunday. Which if you're turning it in on Sunday now, that's got to shift back a week, right? That's when it has time. So, sorry, you guys have coursework. Yes, you do. All right. Last time we were here, 6 months ago, we started looking at series. So we're going to do a bit of review here and get to see where we can go from here. What is a series?
Is
It's a sum of a sequence, okay? For purposes of our class, it is, how long is it?
Infinite.
A series is an infinite sum, okay? And you know, technically sequences can be finite. Again, we're only dealing with infinite sequences here, so this works. But the big thing to take away is it's an infinite sum. Okay, that raises lots of questions about, well, I mean, is that even possible? And some of the times the answer is no, right? And one of the things we sort of learned on Friday, the last time we were here, was that we had this test for divergence. And remember, if the limit, the test for divergence is if the limit as n goes to infinity of just the sequence part, not the sum, but the terms, if term by term, those don't go to 0, then there is no chance that the sum converges, okay? If that does not equal 0, then the sum definitely diverges. Okay, and we should have looked at the harmonic series, the series 1 over n, which is a series whose terms do go to 0, but it also diverges. So when the limit of the terms goes to 0, we're still left up in the air with this big question of, does this thing actually converge? Okay, do I actually get a finite sum, or is it just going through? Okay, so we had that. Otherwise, our only strategy at this point was to look at the sequence of partial sums. The easiest in that category was to look at geometric series, where we could write a formula down for the partial sum. I don't really care if you remember that or not. What I do care is that you remember that if my R value, the number I'm multiplying each time, in absolute value is less than 1, or is between -1 and +1, and not including the boundaries, right? the series converges, let's write out the general term here. And it converges to A over 1 minus R. Okay, and at least one semi-practical application of that, we'll keep it semi, that's fine, is repeating decimals. We can write repeating decimals as fractions, thinking of them as convergent geometric series. Okay. The other one we saw that wasn't as clear, but at least we could come up with a nice formula for the partial sums, is the telescoping series. Where when we started writing partial sums, we got a lot of cancellation on the inside, so we just had some outside terms we really had to test for the partial sums. Okay, like maybe a first term or two, and then a last term or two. And then we take a limit as n goes to infinity, and then we at least knew what happened, right? And some of those converged and some of them don't. Awesome. Any questions about that? Okay, then in this class we started the next section, but my other class didn't, so we're just gonna do this like you've never seen it before, but you have. So the next thing we have is now in section 11.3. I mean, that's a fast summary of like mostly section 11.2. And this is the integral test. So we have another test to tell. So the bad news is that as we're looking at series, it's significantly easier to tell whether or not they converge than to tell what they converge to. So we'll spend lots of time figuring out whether or not sums converge, but then we'll sort of be like, I don't know what it converges to, you know, and just kind of walk away like, it exists, good enough. Okay. So that's it, right? It's a lot harder to tell. And the integral test is our first test that's like that. It will walk away from it knowing, does this series converge or not converge? Does it converge or diverge? But if it converges, we have no idea what the sum is. Okay? So there you go. That's the reality of it. Okay? And so the integral test goes like this. Let f of x be a continuous positive decreasing function. We'll do a comma there with an and. Let f with an integer value equal a sub n. So if you're wondering why are we talking about continuous functions here, we're back at sequences and series. Okay. Then one of two things. Probably shouldn't capitalize that there. If the integral from 1 to infinity of f of x dx diverges, then so does the sum from n equal 1 to infinity of a sub n. Okay, and B, if the integral from 1 to infinity of f of x dx converges, then so does our series. Okay, so the integral test is super nice if I can rewrite the sequence of terms in the series as a continuous function that's positive and decreasing, then I can just look at the integral, and the integral and the series do the same things. So that's pretty sweet. Okay. So we'll do one definite example. Let's do a couple little notes here, sorry, before we do an example real quick. Notes, number one is if the series, oh, sorry, I don't know, if it starts at something other than 1, the theorem works. We just have to start the integral at the same place. Okay. So I don't know, we have to be careful about that sometimes, but it turns out that look, if our series starts somewhere other than 1, then we can start the integral somewhere other than 1 and be fine. Okay. The other one is on this decreasing. Condition. The sequence of terms needs to be really eventually decreasing. Okay, and so if we start at n equal 1, and from n equal 1 to n equal 2, it increases, and then from n equal 2 on after that it decreases, we're still okay. The thought here is we sort of we test the series, the infinite sequence that is decreasing and add finitely more terms. Okay, so if from n equals 3 to infinity everything's decreasing, that's great. Let's test and see if that converges or not. Okay, if it converges, then if I add an n equal 2 and n equal 1 term, I've taken an infinite sum that converges to a finite number, and I've added 2 more finite numbers to it. That's still going to converge. Okay. If it diverges, that means that somehow my sum equals like infinity or something, right? It just gets larger and larger. And so, hey, if I add 2 more terms to it, it still gets larger and larger. Okay, that like it doesn't really affect the convergence. Okay, so that finite number of terms. And that's true even if it's like the first 100 terms. It kind of waves and then eventually it starts decreasing. We won't give you those in class because that would be hard to tell. But like that it eventually starts decreasing, right? But we might give you some that like for 1 or 2 terms, we sort of have this increasing pattern for a couple terms and then it starts decreasing after that. Okay, so anyway, so that's another note that we actually use pretty often. Is like, oh yeah, okay, like so I got a term or two with n equal 1 to n equal 2 to n equal 3, it's increasing, and then after that it decreases. No big deal. Okay. Any questions on those two notes? Okay. Huh. If you like how I asked you a question, turn my back to you, so that if you raise your hand to respond, I could not tell, and then assume that the answer was no. It's a good teaching technique right there. I did need to erase the board, however. Okay. Yeah, we should do. All right. You probably have this one in your notes. I think we did this example last time, but we're going to do it again just because. Because it's the one I have written down that I'm confident in. I have another one written down here that I'm not 100% confident in, and so I'm going to just leave it alone and not make myself confused. How's that sound? Okay. Is that series convergent? I don't know. Okay. Well, look, let's take a look at f of x. We'll make it a function that's going to be 2x plus 1 squared. Is it continuous?
Yes.
At least on 1 to infinity, right? It's actually continuous a lot more than that, but that's all the part we care about. Sound good? Okay, right, there's a discontinuity at x equal negative 1/2. Meh. Is it positive? Are all the y values positive?
Yes.
Yeah, I'm squaring, right? Yes. And is it decreasing? Yeah, because our denominator's getting bigger. Where our numerator stays as 1. Right, and we know that cool thing about fractions, that the denominator gets bigger and the numerator stays the same, then we get a smaller fraction. Great, so now we look at the integral from 1 to infinity of 1 over 2x plus 1 squared dx. We have to decide if that converges or not. So we'll set up our limit to do an improper integral. I've got essentially a u to the negative 2 power, okay? I probably should not do this. Sorry, I should do this. I was going to shortcut it, but I'm not going to. Let's see, 2x plus 1, when I plug in 1, would give me 3. When I plug in t, it would just give me 2t plus 1. So u to the negative 2. There's my 1/2 du. So when I integrate, I'll have u to the negative 1. Still evaluating from 3 to 2t plus 1, and we'll go ahead and do that. Negative 1/2 times 2t plus 1 to the negative 1, and then minus negative 1/2 times 3 to the negative 1. And so just to make sure we can see this clearly, let me rewrite those. Let's do a quick algebraic transformation before we do a limit. We'll take this as negative 1 over 2 times 2t plus 1, and then I have a minus negative, so plus 1 over, it's 2 times 3. And we could simplify this more, but let's go ahead and take the limit. What happens when t goes to infinity? This goes to 0, and so I end up with just 1/6. Okay, oh, we're not done with the problem yet. By the integral test, series from n equal 1 to infinity of 1 over 2n plus 1 quantity squared converges. Right? We weren't really asking about the integral itself. We found that the integral goes to 1/6. That's not really our answer. Sorry. Erase the box. That's what the integral does. And because the integral converges, then we know that the series converges as well. And that's what we're really asking about. Okay? I'm going to leave something for you to chew on because I don't think we have enough time today to do it justice. But we need to establish this. Tomorrow we're going to start learning the comparison tests. And so we need some series to compare with. Okay? And so the question is, for which values of P does the series from n equal 1 to infinity of 1 over n to the p power converge? Okay, and something to notice is you have a partial answer. Note when p equals 1, this is the harmonic series. Because then it's 1 over n. So we know, at least in part, that the answer is, well, since I asked about convergence, not when p equals 1. But after that, I don't know. Okay? It turns out you can tell this by the integral test and by doing some integrals we already did. Okay? 7 or 8 months ago,
Yeah.
we were doing improper integrals. Okay? What's that? You can keep your exams. Otherwise, I end up keeping them for ridiculous amount of time.